We're going to do some practice, just get as many questions under our belt as we can. And I want to talk a little bit about WebAssign and its bad habits. But let's just get into the swing of things by just doing a very basic one. Let's suppose I asked you to do the derivative of 4 cosine x, take away 3 secant x. Now, over here, we've got our little hit list of functions and what their derivative is. So essentially, if you want to know what the derivative of 4 cosine is, you find the derivative of a cosine, stick a 4 in front of it. So it's -4 sine x. And you want to know what a secant is? A secant's derivative is secant tan. So -3 of these is -3 secant x tan x. And that question is finished. There isn't any trig identities or common factors that we could do here that would improve that. So it's finished. It's just a little baby one to get us on the road. How about this one? Right. So we have a power of x and a trig combination. I want to find the derivative of x to the 7. It is still the power rule. On the other hand, would you all agree this is a product rule? Agreed? Now, I am going to do this derivative as a product rule first, and then we'll see what happens. So you get 7x to the 6. If you differentiate a sine, you get a cosine. You leave that guy alone. Plus, you have this guy, and that's a sine x. And you do a cosecant x, and the derivative of a cosecant x is negative cosecant x, followed by a cotangent x. And I'm going to have to write that again because it's far too crushed. So it's this guy plus a cosine x, cosecant x, plus a sine x times a negative cosine x, cotangent x. There we go. I'll take it really slowly. This line nothing really happened there. I guess I didn't really need that line. It's probably taking it too slowly. Okay, let's look at style points. Is there anything you can do with just those 2 trig functions to make them prettier?
Factor out a cosecant.
Okay, let's do that. And if I do that, I get a cosine x, take away a sine x, cotangent x. Now, this is a good example of why trig can bite your bum. It's quite natural to think that that's as good as that's going to get. In fact, you might be suspicious about why it even bothered bringing out a common factor was when it isn't a common factor of all the terms. That's quite right. I probably shouldn't have done that, except for this. Isn't a cotangent 1 over a tangent, but isn't a cotangent also a cosine x over a sine x. That means that we have a cosine x, take away a cosine x, which means we have 0. Which means that the answer is actually that. Do you see how sneaky trig can be? Now you might think, how on earth did that whole thing become 0? Well, if I thought of it as sine x times 1 over sine x, this is in fact 1. And if you differentiate 1, you got 0. So if I had noticed that this term here was actually 1, wouldn't it be just x to the 7 plus 1 I was differentiating, and that would have got me my 0. So the bottom line in these stories when trig is involved is you just have to be on your lookout for identities. Either at the start, where the guy that you've got might not be the guy that you actually use. You know, if I did this at the start, I'd get that. Or later on, when style points happen, you can figure a way of changing it. You just keep going until you can't see anything else, I guess. And it's not a fixed, trig's not fixed. It's not like, well, like x squared plus 5x plus 4, right? We can show you a technique for factoring, right? And there's not anything surprising in there. Now, trig's weird. Two very similar looking expressions in trig. One of them might turn into 1, and the other doesn't turn into anything, right? It's just ugly and it stays ugly. And you can never be quite sure in any given situation what is going on. Oh, let's try this fella. Oops, sorry. Yeah, I'll do it. No, that'll work. Would you agree this is a product drill with a theta squared at the end? So the derivative of theta squared is just 2 theta. Right. This fella is going to be f dashed g plus f g dashed. So differentiate this guy, you get 2 theta. Leave that guy alone. Leave this guy alone. Okay, what do you get if you differentiate a cosine? Derivative of a cosine.
Negative sign.
Okay. Agreed. In this world, I would pull out a theta as a common factor, and I'd get 2 cosine theta minus a theta sine theta plus a 2. And in this situation, I do not need to worry about trig identities. The minute you stick a theta next to a trig guy, like here, you'll never ever join up with a cosine that doesn't have one. Would you agree that these are dissimilar and they're different enough never to have a trig identity that would merge? So it's in a funny sort of way, it's nice if the terms are ugly, because if they're ugly, right, some have theta squared, some don't have any theta in them, right, that kind of thing, that the chances are you won't have any trig identities to worry about. So ugly is good for trig, because if it's ugly and different enough, you won't need to worry too much about sorting it out. Okay. Here's another one. going to be a product rule. Now, there's no guarantee that this guy isn't going to turn into something different because of a trig identity, right? I'm just doing a quick scan through them and thinking maybe I should try it and see if there's anything useful. What I typically do in these questions would be, and before I get too caught up on the process, is maybe spend a few moments just looking at the thing and seeing if I can do anything. And one of the simplest ways to play with trig functions is to turn them into sines and cosines. Would you agree that if you turned this into sines and cosines, you don't get anything interesting? So that probably means that this guy can't be fixed, right? So there's not a little trick at the beginning. On the other hand, let's suppose I was going to differentiate that guy. A secant is 1 over cosine theta, and a cotangent is a cosine on the top with a sine on the bottom. Ah. Can you see that this guy is really just a cosecant theta? And so wouldn't it be easier just to differentiate that by going over to my table and saying that's the answer? And I didn't need to do a product rule, because if I did a product rule, with this guy, eventually it would work, but I would be spending an awful lot of time doing style points just to fix it. Right. So it's worth having a look at an expression and seeing whether or not it might simplify. And the simplest way is turn everybody into sines and cosines and see what happens. And do they play well together? Right? Do they cancel? Or do they not? And if the answers are not, just leave the original alone and differentiate it. So that's where we're going to go. Leave it alone and differentiate it. Right, if you differentiate a secant, you get a secant tan times another tan plus a secant. And if you differentiate a tan, you get a secant squared. Now I'm going to have a secant theta tan squared theta plus a secant cubed theta. Okay, time for style points. Is there anything you can do here to make it a little bit prettier?
Could you factor out a secant theta?
I would. And we would be on the lookout for identities, just in case that is one. It looks like it should be one. A lot of people think it should be one, just like sine squared plus cos squared is one. The answer is it's not any identity at all. In other words, we're finished. So let me show you an idiosyncrasy that is really annoying, but we're going to ignore it and we'll do your thing that your mum said to you. Your mum ever said to you, do as I say, not as I do, right? So sometimes I forget to do this, but you're not. Sure what I'm mumbling about. Here's that question. The correct answer is secant. Now, you want theta, you have to go over to the Greek letters, and it's there. So if you're wondering where theta is, that's it. That's not what I'm talking about. So we've got secant theta, bracket, and what is it? Tan squared theta. Okay. Here goes. Tan. Okay. theta power of squared plus secant theta cubed. Oh. Right.
Your
I would
syntax
like.
is a little bit off.
Okay, how have I got our brackets? Am I short of
Yeah,
a
you
bracket?
need one more in front of the tangent. Because it made it so that it includes the secant.
Okay, so we've got tan of theta being squared plus a secant of theta being cubed. Looks good. Okay, so I'll watch this.
Shouldn't the final secant theta be squared instead of cubed?
Oh, well, that's good. I wasn't expecting that, Cross. Thank you for noticing that mistake. Okay.
When you press backspace, it made it no longer an exponent.
Aren't you glad you get 5 shots? There. Okay. Do you notice that after my third attempt that you can't write tan squared, you have to call it tan theta bracket squared. If you try and stick a square in, it gets uncomfortable about it. That's actually not my major issue, although that's ugly. My major issue is that if I had written in, and I'm not going to attempt it based on my past experience, but if I had written in this line here, WebAssign would tell you you're correct. WebAssign does not do style points with trig at all. Well, it knows if you've done it, but it's not good at just accepting only that. So you might well get into the habit of not doing style points because you're getting your homework right. And I won't, because I don't have the time to go through every person's answer to make sure that they've written the style point version rather than this version. So you're just going to have self-control and do it yourself. Because when the test happens and you do that instead of this, you're not going to get all the points. I'm not going to start bad habits because of software. Just because the software says it's okay to leave it ugly and not do style points on it doesn't mean that's the right thing to do, right? So be aware that WebAssign has got a little issue. Well, I guess it's hard. Can you imagine it's a piece of software and the fact that trig can do so many things that it might be difficult to program it to understand style points in every situation with a trig function. Is there any questions so far? Are we getting okay with the idea of product and quotient now? Right. Just be on the lookout. Sometimes you don't get any problems at all. And sometimes things get ugly. Try to find something ugly. This one looks interesting, so I'm going to pick that. Here is a 1 plus secant W, and it's going to be over a 1 take away secant W. Right, I'm not going to look for any identity that makes that pretty. It's pretty obvious there isn't one. Would you agree? If that had been an identity, I'm sure I would have seen it by now.
I will
It's of
say
course
that
going to be a question.
nothing when I looked at it is obvious to me. Just like I'm going to be really struggling here.
Okay, let me do a side issue then. I'll use theta, but any variable will work. Here are the identities that I expect you to recognize. So if you ever see a sine squared plus a cos squared, it should be 1, okay? But from that one identity, there are 2 babies. What do I mean by that? One of them, and darn it, I should have written it the other way around, but too late now. And I meant in that direction. So if you ever get a trig, you know, you've got your answer and it looks like this fella, right? That is the same as sine squared. And 1 minus sine squared can be written as cos squared. And can you see that what we're doing is we're taking 2 things and making it 1? But actually, you only need to memorize this one, because can't you from this one algebraically figure out these 2? So these are called Pythagorean identities because they come from Pythagoras' triangle, I assume. Right, the next one, and I always get this one back to front, so give me a second while my brain's still thinking. Secant square theta take away tan square theta is 1. If you rearrange this guy, secant square theta 1 tan
We have
squared.
to know why that's true, or do we just, you know, learn the rule?
I can prove this one if you like. You don't need to know why. You just need to
Okay.
know when you see this, you get that. There, I'm going backwards again, but that's just the way my brain remembers these things, I guess.
Should I know why?
If you do a tan, do you want to know why?
Sure.
Okay. Let's take this fella. Secant squared theta take away tan squared theta. Well, I know secant is 1 over cosine, so that's 1 over cos squared. I know this is sine squared over cos squared. Since they share a common denominator, which is cosine squared, I get that. Isn't 1 minus sine squared a cos squared? And a cos squared over itself is 1. So that's 1. Those guys, these are the Pythagorean triples. This one is connecting sines and cosine squares together. This one is connecting sines, secants, I should say, and tangents together. They're not too many. I mean, there is a double angle formula. For some reason, I've decided to turn into x's. So if you ever see 2 sine x cosine x, you will replace it by the sine of 2x. And there is the other double angle formula, which is this fella. But this fella has 3 versions. So if you have done your derivatives, right, and you've worked your way through and you've fought as hard as you can, and you're left with a cos squared minus sine squared, turn it into a cosine 2x. If you've got 2 cos squared x's minus 1 left over, turn it into a cosine 2x. And if you have a 1 take away 2 sine squared x, turn it into a cosine 2x. On the other hand, if you have a 2 sine x cosine x, call it this guy. A secant squared minus 1, call it that. A 1 plus tan squared, call it that. A secant squared take away a tan squared, call it 1. And these 3 guys up here. So those are your main, you should know them. And you should also know that a cosecant is 1 over a sine, a secant is 1 over a cosine, and that a cotangent is 1 over a tan, And a cotangent is a special one because there's two versions of him. He's also a cosine over a sine. So there's your hit list. Those are the major identities that you're expected to know. Now, are there lots of other identities? Sure. But if you come across an expression that you think might turn into something nice, turn everybody into sines and cosines and play with these things. And if it works, a whole load of things will cancel on the top and a whole load of things will cancel on the bottom, and you'll get a nicer answer. And if it doesn't work, it'll just look like a dog's dinner, in which case it probably means there's nothing you could do to that expression. It's ugly and it's still going to be ugly at the end. I'll move these guys over here. Right, back to this fella. I want his derivative. Right, I don't know, did that help any, Teresa, giving you a list of the guys you need to know?
Yeah, that really did. So I'll keep working with them.
Right.
And the idea that I need to just concentrate on getting everything to sines and cosines. And so the answers preferably would be in sines and cosines, if you could.
Well, not so much preferably, just turn things into sines and cosines when you're trying to make it pretty. Right, see if the answer is ugly and it's got secants and tans in it, and you turned it into sines and cosines and nothing came of it, right, it's still ugly. Leave it in the original format. But sometimes when you turn things into sines and cosines, you'll be able to identify other identities, other ways of fixing it, and those are worth it in that case. Right, it's going to be f dash g take away f of g dashed over g squared. The bottom here is basically that guy squared. And I've never ever come across a situation where I would want to do anything with this. Typically, the bottom just stays like that, right? There's no good reason to do anything to it. Right, now if you differentiate 1 plus a secant, you get 0, and the secant guy gives me a secant, what's a W? A secant tan. So that's f dashed. G is 1 minus secant. Take away, leave the top guy alone, which is 1 plus secant. And the derivative of the bottom is negative secant tan. Okay, I'm going to rewrite that guy. Too crushed up. It was a secant tan multiplied by a 1 minus secant. Subtract a 1 plus secant followed by a secant, a negative, almost missed it, secant tan. And the bottom is still there. Okay, distribute this. Let's see what we get. A secant tan times 1 gets me a secant tan. And this guy times this guy gets me a negative secant squared tan. I'm going to have this negative and that negative, so they essentially cancel each other out. So all I need to do is multiply by a secant tan. So I get a positive secant tan and a positive secant squared W tan. God, that's a long expression. Right, is there anything nice going on? Anything cancelled? Anything we can, put together, whatever you want to call it?
I believe secant and then like the beginning, never mind. I thought something canceled out, but never mind, I don't think it does.
It does cancel
No, you
out.
were right.
I just write it there.
Secant and tan.
The secant and tan don't cancel, don't they join together?
Secant
You've got one
square
at one mod.
tangent
Yeah.
and secant square tangent go away.
Right, that one?
Yep.
Agreed? Okay. Now, this says secant tan, this says secant tan, so doesn't that give me two secant tans? I have a quick check, see if there's anything I can do about it. If I turn this guy into sines and cosines and I turn this guy into sines and cosines, can you trust me that nothing good comes of it? It doesn't simplify. So I'm done. So there wasn't really any trig identity to worry about. That's okay. Right, let's work on, whoops, our next guy. Right. And our next fella. Oh, God. Oh. Well, yeah, we've got time for two more, at least. Right, this is 13, or like it. I muted everyone just because I was getting some background sounds. Okay, what you got here? Well, it's definitely a fraction. So to find the derivative of this thing, I'm going to do f dash g, take away f of g dashed over g squared. But in this case, I'm actually going to do some working on the side. Okay, the bottom is 1 plus t, its derivative is 1. The top, the f, is t times sine t. How am I going to find the derivative of t sine t?
Power rule. Um,
That might be the wrong name.
Oh, sorry.
So you might be telling me to do the right.
Sorry. The product rule. Sorry.
There we go. Yeah. That's what you meant, right? Product rule. So yes, we do have a quotient, but isn't this one of these, you have a quotient rule with a little baby product rule inside it, right? That happens from time to time. So I'm going to have to differentiate f, this guy, by using the product rule. So it's going to be 1 times sine t plus t times cosine t. So f dashed is sine t plus t cosine t multiplied by g, take away f, which is t sine t, times 1. And the whole thing is over 1 plus t squared. Right, so if I distribute this, I get sine t. That guy gets me t sine t. That guy times 1 gets me t cosine t. And that guy times that guy gets me t squared cosine t. And that guy there is just a takeaway, that fella. And it's over 1 plus t squared. As I scan through it, I can see one term that'll cancel out another term. Can you see the guy I'm talking about? Somebody gets cancelled by somebody else.
T sine t.
Who gets killed? Yeah, that guy gets killed off. So what am I left with? Because I'm a picture straightener, I'm putting that guy first, putting that guy second, and I'm putting that guy third. And I'm going to do it as a 1 plus t squared. And I'm going to look at that and I'm going to say, that's as good as that's ever going to get. So I'm finished. Have you noticed that you don't need to know any trig identities for at least half the questions? In other words, whatever the answer is, pretty much that's what you end up with, right? There isn't anything too sneaky. But you know, it's always the ones you're not thinking about that come and sneak up and bite you. Like, you did 4 questions and the answer was the answer, right? You didn't really do much. And then question 5 comes up and you don't realize there's an identity going on. Now I'm picking this one because I kind of like it. And I kind of like it because it's 3 things multiplied. And we don't get many practice at 3s. We do 2 things multiplied a lot, right? But we don't really do 3 things. And we did yesterday the derivative for a 3-way multiplication. Can anybody go for glory and tell me what that formula was using FGs and HGs?
F prime. Oh, Ethan, you can do it. Oh, go ahead. It's fine.
Okay. F prime G H plus F G prime H plus F G H prime.
Great. The only thing that's wrong with that is you're using the word prime, and you should be using the word dash because that's what it is. But obviously, you're probably the same type of people who would say Z instead of Z. I'm still working on that, obviously. Do you think I should just take points off when people say Z instead of Z? Would that be a good way of encouraging proper pronunciation?
No, I'm
What
gonna
do you
lose
think,
points
Ethan?
daily.
You can do that in
Okay.
Scotland, though.
The thing is, Z is a letter, Z is a word.
Where did you
I
come up with
actually end
that
up
silly
saying
idea?
That is also clever.
Z is a word. Z is Z-E-E. Z is a word. Z is a letter. You just got it back to front. That's the only problem you have. Can't take your lot anywhere. You would be an embarrassing in Scotland. When you're doing your alphabet and you did that, people would say, doesn't even know how to say the alphabet. How bright can that person be? Okay, let's get this show on the road. You get a 1 and leave the other 2 alone. Leave the middle alone. Sorry, leave the beginning alone. Differentiate the middle. Leave the end alone. That's that one. Then you have F, G, and the derivative of sine. So what am I looking at here? I'm looking at a sine theta, cosine theta, a negative sine squared theta, and a plus cos squared theta. Now you could put that into WebAssign and it will tell you you're correct. It will say, yep, I agree with you, you got the right derivative. This is not one of those questions. This one has some more style points in it. Now, I cannot pull out a common factor, but I can do it if I only use those 2. And I'll pull out a theta, and I'll have a cos squared take away a sine squared. Does anybody recognize that guy? Because I wrote him down today.
That equals 1, right?
Mm-mm,
Was it a
you
negative
almost. If it was a plus, you'd be right.
-1?
Nope, that would be correct if they were both negative cos squared and a negative sine squared. That would have been -1. You're right if that had been the case, but it's not that, so it's not right.
Would it be cosine of 2x?
Or in this case, theta.
Yeah, sorry.
Now, yeah, I know what you mean, right? That guy and that guy. Would you agree that this one is simpler looking? That's the whole goal of trig style points. If the guy you write down has less stuff in it than the guy you had before, then you have done some style point to it. Now, do you see in this case, it wasn't obvious that there was even a possibility that you could do better. And added to that, the fact that WebAssign is going to tell you you're right, you won't even know that you're wrong. You won't know that that's the correct answer because WebAssign will say, fine, yeah, you're great, not a problem. I'll take that. So you could do 3 or 4 questions where nothing happens, right? You do the answer, what you get, you know, whatever that is, works fine, finished. And then the 5th one comes along and something sneaky happens. So you have to kind of just have one of those, it comes through experience, where you have one of those kind of suspicious minds. Be suspicious that there might be an identity there. Chances are there isn't. But just be suspicious and say, if there was one, where would it be hiding? Well, I know I can't do anything common factor to 3 of them, but these 2 guys look kind of similar. I wonder if I pull out a common factor theta and see what's left. Oh, I've seen this guy before. Bingo. It could have been those 2 guys positive, right? In a different world, right? In a different question, couldn't we have been left with this guy? Right, and some other stuff. Well, I'd pull out the theta, and I would have seen sine squared plus cos squared. Oh, that's 1. And so I would have had whatever that stuff there is, plus a theta. You see, it would have went that route. And then it might be nothing, right? You pull out the theta and there's some stuff there and there's nothing going on, right? It isn't one of the typical identities that you're expected to know. In which case, that's fine. Leave it alone. Just leave it alone. Call it good.
Why does that just turn into theta?
Oh, sine squared plus cos squared is 1. So it's theta times 1. So it's theta.
Gotcha. Okay, thank you.
I have a question.
Yes.
Okay, so if you factored out the theta and it wasn't a trig identity, would you, for your final answer,
Yes.
would you leave the theta factored out or would you put it back in?
Don't care. They're both correct. Whatever you feel like. If you've went to all the trouble to write it, you might as well just write it down. You know, yeah, there's wiggle room there. Me personally, I wouldn't bother just because I'm lazy. Because I do my check on a piece of scratch paper and I only write it down if it did anything good. And if it didn't do anything good, I just leave my answer, you know, like that. So I go to a bit of scratch paper and I just focus on this and I have a look at that and I see if it turns into anything. Oh, it does, in which case I would write this down. But if I did this and nothing interesting happened, I'd say, well, I'm not doing anything. I'll just leave it like that and call it good. So that's just my preference. But if this didn't work, this is correct and this is correct. You won't lose either way. I think we have come to a very natural finishing point. Say hi and bye-bye. And that list that I gave you, be a great idea if make a nice neat card and have it stuck beside you when you're doing these questions so you can have a quick look each time just in case something's floating around that might be nice. And the best thing is if you can memorize the darn things, because if you can memorize them, you don't even need to look at the card. Your brain will just say, hey, that's 1, or that's the sign of 2 there, or whatever it is. Okay, bye-bye, guys.
You all have a good weekend.
Thank you so
Thank
much.
you.
Thank you.